So here's just an interesting paper that I think is, oh, I didn't share. Okay. So economists are often kind of like dragging on about taxes. They're like, it would be great if we could lower taxes. It would be good for the economy. It's for the economy. So this is just a little paper about why some of the kind of research about why economists drone on about taxes so much. So what these guys do, this is Judd Kessler is a professor from Penn, where I went to graduate school, and Michael Norton is his friend who's at Harvard. And what they did is they just brought in workers into a lab, and then they varied how much in taxes they put on the worker. So the worker might pay a 10% tax or 20% tax. And what they find is actually that people work much less under any tax than they would an equivalent wage reduction. So it's not just that, like, oh, instead of paying you $20 an hour, the tax is as if we're paying you $15 an hour. It's as if we're paying you much less than that, because people don't like kind of being used for taxes. So they call this result a tax aversion. They say it's large in magnitude. When we decompose the productivity reductions that arise from taxation, we find that 40% is due to lower net wages, and the remaining 60% is due to tax aversion. So part of it is due, you would get less production if you reduce wages, but over half of the effect is just due to the fact that people don't like working under taxes. So this tax aversion affects labor supply more on the extensive margin than on the intensive margin. So this is an interesting economic concept that I'll tell you. So the extensive margin is whether I work or not. So the extensive margin is whether I am leaving the house to go to a job or something like that. The intensive margin is how much I work, how productive I am while I'm actually working. So what they find is that labor supply is reduced more on the extensive margin, which means that people just work less rather than that they're being less productive while they work. So lots of people kind of just work less when taxes are high, and then while they're working, they're less productive. So that's just an interesting kind of example of the kind of research that people do in labs, and we'll come to why these kind of experiments are really useful today. Actually, we'll work on that today. Any questions on that? Is that or on material from yesterday or before? There we go. Okay. So today we'll be talking about endogeneity. And endogeneity is a fancy word, the Latin meaning endo is within. So like an endoskeleton is a skeleton that's inside the body, an exoskeleton is a skeleton that's outside the body, like a lobster. And gen is to make, to produce, or to be born. So all this means is basically the endogeneity is when something is being made within the system, And basically when we have a regression and the variables are related within the system in a way that is not exogenous, we can have bias in our regression. So that's what we're going to talk about today. So there are three kinds of endogeneity, and we've already talked about one of them. The first is omitted variables bias. So remember, we talked about that right before our first test, our midterm. And omitted variables is when we have an omitted factor affecting y that is correlated with our x of interest. So what does that mean? It means that there's a variable that is basically within the system that we're not able to control for. The second kind is kind of fun. We'll think about it today. It's called reverse causality. So sometimes we have this problem where we think that x causes y, but also we think that y causes x. So when we do a regression of y on x, it's going to be complicated because they're related within the system. The system is generating, x is generating y and y is generating x. So a classic example is that we think that police reduce crime, but we also think that if crime increases, cities hire more police, so that crime actually causes an increase in just the number of the share of population that are police officers. And then the last one is measurement error. And we talked about this a little bit the other day with outliers. So when we have data that are, when the data are mismeasured, that's what measurement error is. And all three of these are examples of endogeneity. And they all make our betas biased. They make it so that when we estimate a relationship between two variables, we're certainly not getting the causal relationship if we've got these going on. So when you and I are interested in, studying something, we'll often be wondering when we see a paper, is there measurement error? Is there reverse causality? Are there omitted variables? So the thing I just showed you, where basically these researchers bring in workers into a lab and they experimentally vary what the tax rate is or what the wage is. Let me just bring this in right now. So experiments don't suffer from endogeneity, which is to say that the treatment is exogenous. It's coming from outside of the system, exogenous. So what does that mean? It means that the treatment is not correlated with omitted variables. There's no omitted variable bias. The treatment is not affected by the outcome because it's randomly assigned, so it's not affected by the y. And hopefully, because we're running the experiment, we can have good measures of whether someone is treated or not. So an experiment is going to basically kill all of the kinds of endogeneity that we might be worried about. So experiments are kind of the gold standard. They get rid of, they're kind of like Mr. Clean. They get rid of endogeneity. Okay. So in words, endogeneity occurs when an explanatory variable is correlated with the error term. When the error term is correlated with the x's. So that is, there's something that, remember that the error term is all the stuff not in the model. Endogeneity causes the coefficient to be biased. So that's the bummer of it, is that when we have when stuff in the error term is correlated with the x's, the betas that we're estimating from this regression will be biased. They'll be the wrong value. They'll be a value that doesn't reflect the truth. Yeah, bias is when an estimate doesn't reflect the truth. Endogeneity makes the causal interpretation of the coefficient invalid. So whenever we have an endogeneity problem, the causal interpretation is wrong. We don't think that the beta reflects the causal impact of an x on y. So let's look at why x1 can't be correlated with u if we want a valid estimate. So actually, let me just pause here and take questions. Let me see what questions people have. Esmeralda, Ibrahim, Katrina, Kim, Leana, Levi, Manuel. Okay. So let's look at why x1 can't be correlated with u if we want a valid estimate. So suppose that the u is correlated with x1. And remember, u is just everything that affects y that's not in the model. So if u is correlated with x1, we can write it like this as a regression, where we've got u is a function of x and our parameter values, delta naught and delta 1, and then an error term, which is just where x1 does not predict the u. And we have done this before, actually, where we plug in, so we have this y, and there's a u here in the true model, and there is some, we're going to be able to plug this u in right here. And that's where we're getting this term. And then we're going to collect the terms. So we have delta 1 x1. We're going to put this so that we can factor out the x1 together. We're also going to have a common, two constants. So we're going to be able to group these constants together like this. So we have all the constant terms together. We have all the coefficients on x1 together. There's only one coefficient on x2. Now those are together. And then we have the remaining error term. And what we've seen before, and I'll show you again, is that this will be the beta naught that we estimate if we haven't controlled for x1, if we haven't controlled for whatever is in the error term. This will be the beta 1 that we can actually estimate if we're not able to control for whatever's in the error term. It looks like here our beta 2 and our beta 2 star will be the same value. So what do we learn? We learned that if the x1 is correlated with the error term, then we don't get the true beta 1 when we run the regression. So what if u is not correlated with x1? What do we get? Well, if u is not correlated with x1, let's just go back to this box right here. If u and x are not correlated, then this delta is 0. That's what to not be correlated means. It means that the coefficient on x1 in a regression of u on x is 0. So what would happen is that this delta down here, delta 1 down here, would be 0, and the beta 1 that we estimate would be the same as the true beta 1. So it's only when there is actually a correlation between the X1 and the U that the bias enters the problem. Okay. Questions here? Okay, so we've talked about these three sources of endogeneity. We're going to go through them more slowly now. So omitted variables is the one that we've seen before. And we start with the true equation where we say we know that y is a function of x1 and x2, but for some reason, x2 is not available. So why could that be? It might be that x2 is hard to measure. So for instance, like measuring personality or measuring beliefs or measuring values or measuring even ability is hard. There's a lot of dimension, and it would be very difficult to test everyone's various abilities and have that in a big data set. So the equation that we estimate, because we can't observe x2, is limited, and we call this a restricted model where there is no x2. No x2, we don't have it, so that makes us sad. So now we're going to suppose that x2 and x1 are correlated in this following way. We've got x2 is equal to, this is the y-intercept of the relationship between x2 and x1. This is the slope parameter between x1 and x2. So this is only a positive or negative value if x1 and x2 are actually positively correlated. And then here, eta is everything that affects x2 that is not x1. So everything that's outside of the model that affects x2 is in eta. Okay, so it's like the error term, but for this other regression. So what do? We can actually say, we actually know what we can write x2 in terms of this regression that we just drew, which is delta 1 plus delta naught plus delta 1 times x1 plus eta times beta 2 plus epsilon. So that's where this is coming from here. This is just the same as the value of x2. So then what do? We're just going to collect the terms. So all of the things that are going to be constants will go together. So for instance, we'll just multiply this beta 2 through the whole item in the parentheses. And then that's all this is. It's just basically all the additive terms. And then we're going to group them together. So we've got, these are constants, by which I mean they don't have an x in them. So we're going to put them together here. We have, these are all of the terms that include an x1. So we're going to put those together here and factor out the x1. And then the error terms is everything that's basically interacted with one of the errors, either the epsilon or the eta. We're going to put those here. Okay, so instead of estimating beta 1, we estimate this. So the beta 1 that we're able to estimate is the true beta 1 plus a bias term. Okay, so the bias term, notice this. What is delta 1? Delta 1 is the relationship between x1 and x2. If it's 0, if there's no relationship between x1 or x2, the bias term disappears. It cancels out as 0, and the beta we estimate is the true beta. If beta 2 is actually 0, so that is to say if x2 does not affect y, then also this term cancels out, and the beta 1 that we estimate is equal to the true beta 1. So what does that mean? It just means that this has to be, that that to have omitted variables bias, we need two things. Let me clean. Clean. Let me just clean this whole thing. Omitted variables bias requires two things. One, that x2 affects y, and that x2 is correlated with x1. Okay, so if either of those are not true, then there's no omitted variables bias. You have to have both of those be true for there to actually be a bias problem. Okay. So actually, let me just pause right here. So you've seen this before, but this is just, I'm not going to ask you to derive this, but it is useful to see where it comes from. I think that the understanding where this comes from is actually really clarifying. And that formula is super important. That was on the midterm, and that will definitely be on the final. Any questions? Noah, Saul, Stephanie, Warren, Yesenia. Awesome. Okay. Well, break in when you have a question. When something seems foggy or I'm stating something that doesn't seem clear, break in and tell me. That's the most charitable thing you can do in this class, is probably to break in and tell me when something doesn't make sense. Okay. So the truth is that when we're not doing experiments, we usually have omitted variables bias. Almost every regression that we've looked at in this class so far has had some kind of omitted variables bias. So when we looked at the effect of education on wages, we were omitting ability. When we looked at the effect of pollution on house prices, we were omitting whether a place was rural or urban, which is correlated with pollution and affects housing prices. When we were looking at the effect of profits on salary, we were omitting the size of the company. So a bigger company is going to have different kinds of profits, and it's going to have an independent effect on the CEO of the salary. So let's think about this a little bit more. So that's the first kind of endogeneity, is omitted variables bias. So I might ask you on the test, what are the three kinds of endogeneity? And it's omitted variables bias, reverse causality, and measurement error. Okay. So reverse causality is sometimes called simultaneity, which just means two things happening at the same time, simultaneously. So if the explanatory variable is a function of the outcome variable, then it will be correlated with the error term and therefore is also biased. So suppose that we're trying to estimate the effect of police, the number of police you have in a city, on the amount of the crime rate in a city. So we're interested in, you're a mayor in Seattle or Baltimore, and you're interested in knowing, if we hire more police, what effect would that have on the crime rate? The problem is that the number of crimes, if you were going out into the world and collecting data, the number of crimes in a city is also affecting the number of police that they hire. So we are likely to get a beta in this regression that's biased. That's not the true effect of police on crime. So let's do some more examples of that. Okay. So what does this look like? This is essentially that we have y, the crime rate, as a function of x's. But we also have that x is a function of y, which is to say that the number of police that we have is a function of the crime rate. So they're affecting each other at the same time. So the outcome variable y is a function of x. However, the explanatory variable x is also a function of y, and it causes this circle, like we saw in this last figure, where crime is causing police, and police are affecting crime. So it's kind of circular issue where x is causing y and y is causing x. This causes the x's to be correlated with the error term and thus bias. So if we basically we could put, let's just see if this makes it. So we have this regression, y equals beta naught plus beta 1 x plus u, and we know that x is a function of y. So we basically have that y equal to beta naught plus beta 1 times, these are called, these cool letters are called gammas. Gamma naught plus gamma 1 y plus epsilon plus u. So we have that this is obviously going to be correlated with the u. I'm trying to think how to show that, because I don't know. I have to think about that a little bit. I'll think about it some more after class, just so I don't waste time. Okay. So in each of the following examples, causality could be going in both directions, which would bias our estimate of beta. So we've done the crime and police. So we think that police are affecting crime, and that crime is causing a city to hire more police. We think that fitness is going to make you more likely to be an athlete, but also being an athlete is going to affect your level of fitness. You'll be exercising more. We think that teacher quality affects student outcomes, but it may also be that higher achieving students make it nicer for people to become teachers, so that student scores could actually affect teacher quality. You could imagine that, like if I was living in Philadelphia before here, and the schools are so rough that the teacher attrition is just over the top. Just they're just kind of always cascading out of schools because in these urban areas, because the setting is so difficult for teachers. So here's let's do a little example. We have company profits affecting CEO salary. And we're a little bit wondering two questions. Is there an omitted variable that we should be controlling for? And does CEO salary also affect company profits? So what omitted variables might we have? What do you guys think? Are there any omitted variables here? Cameron, Denelson, Derek, Devin, Esmeralda, Ibrahim. Okay, no, yeah, so I could imagine no. But can any of you think of something that might be correlated with company profits and also affecting the CEO salary? Revenue, okay. Revenue is a good one. Revenue. So there's any omitted variable X that might be correlated with profits that would affect CEO salary. So I'm thinking maybe company size. Revenue would have gotten you there too, actually, company size. So what's the idea? A bigger company might have larger profits, but also a larger company will be paying more in CEO salary. And it could have to do with the company size, not necessarily just the profits. Capital, sure. So capital might be something that's correlated with profits and also affect CEO salary. I could imagine that. Yeah. Capital. I wonder if just like where you are, like say you're in Norway or the US, and maybe Norway has limits on how much you can pay your salary, your CEOs, and also being in Norway is correlated with a company's profits. That would be just place might be an omitted variable. Place. Where the company's located. Company location, exactly. Worker wages. Worker wages. Yeah, I can imagine that. Wages are being correlated with profits and also potentially affecting CEO salary. I can imagine that too. These are good. Good examples. Okay. Is there a reverse causality problem? So can you guys think of any way in which the salary is actually also affecting company profits? Leanna, Levi, Manuel, Noah, Saul, Stephanie.
Expense.
Say again.
Expenses.
Say it one more time.
Expenses.
Expenses. Okay, perfect. So the CEO salary directly reduces profits, right? So if I pay a CEO an additional dollar, profits fall by $1, right? Because the CEO salary is a cost. So there is this kind of mechanical relationship between CEO salary and company profits. That's a very good insight. Are there other ways in which the CEO salary could affect the company's profits? Stock. Let me think. So yeah, let me write it down. I think that's right somehow. Let me give you one other example. What if the CEO salary were really low? Can we get a good CEO for the company? Can we get a good manager no? So or say we're able to pay a CEO a lot of money and get a really great manager to whip us into shape. So you can also imagine that that CEO salary is affecting company profits through the quality of the CEO you can hire. Okay, so maybe you could get a much better CEO if you pay them, because you're basically paying a slave. Those people, CEOs of successful companies, they do not do anything other than work. So you're paying for a slave. You need a very hardworking, very smart, clever slave. What if the company is private? How would stock affect it? So I'm trying to think about the stock thing. I haven't been able to figure out. Salary could affect your stock options. Like maybe if you get a lot of salary, you don't get as much stock. If you don't get as much stock, the company, the CEO is less encouraged to promote company profits. But that's all I've got. But let me see here. CEO quality affecting profits. Okay.
It's like a weird like a chain, because like if the CEO like quality is good, then the CEO's salary is also high, and
Mhm.
then if the CEO's salary is high, then they perform better, then the stock is higher, and then the stock higher, then they give more profit. It's like something like that. I'm not sure
Yeah,
if that
yeah, it's
makes sense.
complicated. No, that's good. I think I'm just brainstorming and thinking of wait, because I think that this is right. That this is just a more complicated story. Yeah, I think that's good. Okay, sounds good. Good thinking, you all. Okay. Okay, this is another great example. So we think that earning more money affects your consumption. Are there omitted variables that are correlated with income that also affect consumption? Question mark. And do we think that consumption might also affect income? So we'll do those. Question mark. So what omitted variables might we have? Things that are correlated with income that affect consumption. Expenses. Okay, let me think. Expenses are correlated with income and they affect consumption. That's right. That's true. That's good. So if you have really high rent and that's correlated with income and your high rent affects your consumption, reduce your consumption. That's true. That's good. That's a great example. Let's see. Yesenia, Warren, Stephanie, Saul, Noah. Number of people in the family. Yep. Okay. So family size. That's a great one too. Family size. Family size could be correlated with income and also affect consumption. Savings. Good. Very good, actually. That's a great idea. That's a good one. Savings, investment. Yep. I had also thought of like a subsistence, or like farming. So like being a farmer is correlated with your income and it also affects your consumption. So you actually might have very low income, have plenty to eat because you're making your own food. But these are actually much better than my idea. Okay. Is there likely to be reverse causality? Location. And thanks for that. It's a great idea too. Location. Can you guys think of any way in which consumption would affect your income? Consumption affect your income. Yeah, that's a pretty good. Okay.
Like for location, it can affect both. Like if we say consumption affect the income, location can affect
Yep.
like
Yep.
the money that the goods that we
Yep.
buy and all that.
Yep. So one good example is you could consume an apartment in the Bay Area where tech wages are higher. So what you consume or how much you consume is actually affecting your income. Another example in developing countries is that some people are not in the United States, but usually in parts of Africa, parts of developing Asia, where when you introduce more calories, they become more productive. So it's kind of a poverty trap where like if you're so poor you can't eat, it's actually hard to work. So maybe through hunger, okay, or something like that. That low levels of consumption can affect your income. Luxurious investment, yes. If you spent money on It's not an investment if it's luxurious. That's true. That's a truth. If you are consuming on luxury, yeah, I could imagine that kind of thing. Any kind of consumption that might affect your productivity, or like I think about like drugs. If you're consuming a bunch of drugs, it would reduce your income. I had this wonderful, nice student, and he was doing so many drugs, his brain just became impossible. If you write it off as an investment. I think consumption. Yeah, I guess that makes sense. So if you are consuming stuff that counts as a tax write-off, that could affect your take-home income. Yeah, that's a good idea. That's a good example. Okay. Yeah, I really encourage you not to do drugs. It's very bad for your mind. About 80% of my friends from high school, they went to Berkeley and they did so many drugs. I couldn't talk to them anymore. They couldn't keep their thoughts together. Okay. Okay, so the last kind of endogeneity is called measurement error. So measurement error is when the observed values in the data are larger or smaller than the true values. So this causes a lot of problems even when the measurement error has a mean 0 and is not correlated with the x's or the y's. So we call this classical measurement error when, where's my marker? When, what is the error here? The error is just, like sometimes it's a little positive, sometimes a little negative, sometimes it's 0, but it's just making it so that we're not seeing the true x, we're seeing some mismeasured x. So sometimes the value is 10 and it's in the data as 11. Sometimes the value is 5 and we see it in the data as 4. So this is called measurement error. And measurement error in the explanatory variable, that's an x, will cause attenuation bias. So that means that the estimate that we produce will actually be too small in magnitude. It will be closer to 0. It kind of shrinks everything towards 0. And I'll show you why that is right now, I think. So first, let's just talk a little bit about some math. So we assume whenever we do a regression, we're actually choosing betas so that the error term is not correlated with the x's. So this is true based on how we choose the betas. When we have the variance of x plus some disturbance term epsilon, that's equal to the variance of x plus the variance of epsilon plus 2 times the covariance of x times and epsilon. So this is just a kind of a property that comes up over and over, and it's been proved by statisticians. And because here we have this term, we know that that's equal to 0 because of our first assumptions. That's where that's coming from. This cancels out, and so we're just left with the variance of x plus the variance of epsilon. Okay. So then this is one more property, that the covariance of x plus epsilon and y is the following. The covariance of x and y plus the covariance of epsilon and y. And what do we have here? We have, why is that? Let me think here. So this is also 0. I think it's because the epsilon won't be, we choose the betas so that the epsilons are neither correlated with the y's or the x's. I think that's right. So that's why this is going out. So we just have the covariance of x plus epsilon and y is equal to the covariance between x and y. So we can use these ingredients to demonstrate that when we have measurement error in x, it makes our estimates smaller. So remember that when we estimate beta 1, it's the what that is actually the covariance of x and y divided by the variance of x. Okay, so what we're going to do is calculate what does the estimated beta look like when there's an epsilon in there, and how is it different than the true beta, which has this form. So so on the top, we're going to look at the top first. The covariance of x plus epsilon and y, we learned in the previous slide, is going to break down like this. So we've got covariance of x and y plus the covariance of epsilon and y. And this is equal to 0. So this will cancel out. On the bottom, we know that the variance of x plus epsilon is going to break down like this from the previous slide. Okay, so we're going to have variance of x plus the variance of epsilon, and then we know that the covariance of x and epsilon is 0. So this is going to cancel out as well. So what do we have? We have this is the result. Okay, so the beta that we estimate will be the covariance of x plus and y divided by the variance of x plus the variance of epsilon, where the variance of epsilon is the measurement error. And that will be less than this formula. How do we know that this is less than this formula? Can anyone see it? How do we know that this on the right is greater than this on the left?
Because the denominator of the left side has the add variable and then the term. So if we add together and we divide the numerator by anything that's big, then we get a smaller number.
Perfect. Okay. Exactly as Liana said. The numerators are the same, but the denominator on the left side is larger. So we know that the value on the left is smaller than the value on the right. And so the beta that we estimate, beta naught, beta 1 star, it will be less than the true beta 1 that we want to estimate. Okay, so that's key. So the key here, if you remember one thing from measurement error in x causes the estimated coefficients to be too small in magnitude. They're too close to 0. So let me pause here and take questions. Cameron Dennelson, Derek Devon, Esmeralda Ibrahim.
Why do we take the magnitude?
So the covariance could be positive or negative. So if this covariance is negative, for instance, then wait, let me see. Yeah, so if this covariance is negative, we've kind of assumed that the covariance is positive, but if the covariance were negative, then we would actually find that this is larger than the true beta because the beta would be negative. So the beta that we estimate would be a smaller negative number, so it would be larger. So I think we've made it a little bit simple by kind of assuming that the covariance between x and y are positive. But when we have a negative covariance between x and y, the results are different, and it's just because the measurement error is pushing any estimate we get closer to 0. So in big measurement error problems, you will just get noise. So there could be tons and tons of data, and you think that there's a really good reason for an effect, but you'll get just mush, just nothing. Does that help at all? Any other questions? Okay, so why do we have measurement error? Well, usually our measurement error is in surveys. So people don't remember what they've done in the past very well. It's called a recall bias. If I asked you what you did how many hours you spent studying last week, and I somehow had a measure of how much you'd studied last week, those two numbers would be different probably. So there's a very famous study called the National Longitudinal Survey of Youth, sometimes call it NLSY, N-L-S-Y, NLSY. And they survey young people about their schooling, about their training, about their income, their hours worked, how many friends they have, all that kind of stuff. And that allows us to study how people grow up. And so say we had schooling, how much they went to school, but it had an error term in it. And we were trying to predict the effect of schooling on income. We're going to get a beta 1 that's too small. Beta 1 will be understated usually. Okay, so how do we fix it? Well, there's not a great fix, but one thing that we could do is get data from each person's high school and employer to verify their actual responses. Administrative data is much less likely to have measurement error. So there's a huge movement in economics and other research to use administrative data sets because we don't worry so much about the measurement error problem. Another problem with surveys is that people sometimes lie a little bit. So you sometimes, so imagine that you're being surveyed by a pretty girl. You might exaggerate how much money you make or whether you live with your mom or whether you have a job. Or even if it's not a pretty girl, you might just think, oh, I don't want this person to think I'm a bum. So sometimes they're not that reliable. Okay, so administrative data, we have data entry mistakes. So sometimes there's administrative data and it still has problems. What we tend to do is called data cleaning, and we look for data that's likely to be a mistake and either fix it or omit it from the analysis. So we could see, for instance, if there's someone that says that they're working more hours in a week than there are hours, we could say that looks like an error. We could see, oh, look, there's a college student that says that they were born in 1919. Well, it's just pretty unlikely that someone that is 121 is in college. So this will actually happen. You'll see, if you ever get into data, you'll find people that were born in, like they say they were born in the 1700s or something like that, according to their administrative data. A really useful thing is if you have double measurement. So I have a project right now where we have survey measures where we say, how many hours did you work or did you have a job? And then we also have administrative data that shows whether an employer could log that this person was working for them. So that's really powerful. It allows us to have two ways of measuring whether someone was actually employed. And then what you do is you either drop observations where they're not the same, or there's some other kind of more technical stuff that you can do, or you use the average of the two, and that actually does a lot of good for getting rid of measurement error. Okay. So how do we fix it? So these are kind of the central focus of an economist's attention is how do we get around these endogeneity problems to estimate effects that we think actually matter. We do not care about the biased effect of education on wages. We care about the true effect of education on wages, because if we're cutting education or we're expanding education, we are doing so because we think we know the actual effect of education on outcomes. So in the past, we would try to just collect as much information as possible and use those as controls. But it turns out that no matter how many controls you put in a regression, there are always things that you weren't able to measure or you weren't able to incorporate. And so what economists now do is they try to find experimental ways of estimating the effect of different treatments. So the gold standard is typically an experiment where we literally randomly assign Okay, these 100 kids are going to a special education program for preschool. These ones are not going to go to preschool. Sometimes we can find places in nature that look like experiments. So remember, we talked about an example in which students were randomly assigned to go to charter schools based on whether they won the lottery, which is random. So that's a great example of a natural experiment, that there's a lottery that randomly assigns whether you're admitted or rejected from a charter school. There are other examples of these kind of lotteries in the world. In years that there are too many applicants for H-1B visas, which is a visa for very highly educated immigrants, they use a lottery to determine which applicants will be admitted and given a visa. A regression discontinuity, and then there are other kinds of natural experiments that are fun. A regression discontinuity, we'll talk about this next week, is basically where there's a treatment that that is provided based on a discontinuous outcome. So I think like the classic example is, it used to be that if you got a 1400 on your SAT score, you were given a national merit scholarship. Okay, so if we wanted to know what's the effect of the national merit scholarship on students' college attendance, we might plot 40%, 20%. We might plot the attendance rate of students along their SAT score. And when that 1400, when students cross that 1400 threshold, they get a scholarship. And so what we will do is we'll tend to say that this effect here, the difference between the line you predict here going to 0 to 1400 and the line you predict here going to 1400, is the effect of the National Merit Scholarship on attendance. Okay, so that's a really convincing design, because the person that gets a 1400 on their SAT and the person that gets a 1390 on their SAT are very similar, but one of them has this big infusion of scholarship money and the other doesn't. So they're kind of as if there's an experiment going on. And then the last thing that I'm not sure that we'll get to it in this short block, but it's called instrumental variables. So for instance, these are variables that affect an outcome, a treatment that we're interested in, and that don't affect the outcome. So one fun example that people have done is they are interested in political, so voter turnout, where the variable here is protests. And so obviously there are omitted variables here. If we just did this simple regression, there's something called enthusiasm, political enthusiasm, that's affecting the size of protests and also the voter turnout. So what we need is something that affects protests, that doesn't affect voter turnout directly. And what they do is they use the fact that if the scheduled protest was on a rainy day, the protests are smaller. And what they find is that protests that were made smaller by rainy days actually predict lower voter turnout in the next election. Okay, and that's clever, because it's not using the variation in protest from enthusiasm. It's using the variation in protest that arises from weather events that are not related to voter turnout. Okay, so that's all I've got for today. Let me stop here and take questions. Kimberly, Leanna, Levi, Manuel, Stephanie's, Lauren, Yesenia. Any questions? Okay, so let's do this. Let's take a break. We will start a new homework assignment together in the second hour. And we might not finish it today, but we will. It won't be due until we finish it together. Okay. So take a little bathroom break. I will be right back. So this was uploaded as assignment 5 in on Canvas. And so the first, basically, this is just kind of a bigger example of what we've done before. So we'll do it together. So the true relationship between y and 3 explanatory variables can be written as follows. Y is a function of x1 and x2 and x3. However, we don't include the variable x2 in the data. So we instead estimate this restricted model that excludes x2. Okay. The relationship between x1 and x3 at the omitted variable and the other two can be expressed as follows. So we've done this before where we have the omitted variable and we express it in terms of the other variables. So first, it asks to derive expressions for beta naught star, beta 1 star, and beta 3 star. So what are these? These are the estimates that we'll get from the restricted regression in terms of the true betas. So what do? We're going to start by, like, this is what I would do, is I would start with a y equals to, what's the model we're estimating? Beta naught plus beta 1, x1, plus beta 3, excuse me, beta 3, x3 plus eta. And actually, I'll do it this way because we just did it this way in class. So I'm going to do a little bit on the fly. So the true model is like this: beta 2x2 plus beta 3x3 plus what do we have? U plus U. We're going to, because we're omitting x2, we're going to put in this for this, and then we're just going to collect the terms, multiply beta through and collect the terms. What we have instead is y equals beta naught plus beta 1 x1 plus beta 2, and then we're going to plug in x2, which will be delta naught plus delta 1 x1 plus delta 3 x3 plus epsilon plus beta 3 x3 plus u. Okay. And so we're going to start collecting terms. I'm going to just use colors to collect terms. So first, we want all of the constants together. So we're going to have beta naught plus beta 2 times delta 1 will be one constant. We're going to have all of the variables that are have a coefficient on x1. So that's going to be beta 1 x1, beta 2 times delta 1 x1. And that's it. and then all the variables that have an x3 in it, all the coefficients that have an x3 in it, okay? And then the last is just, we'll group all of the error terms together. So what do we get? We will get beta naught plus beta 2 delta naught. So this will be our beta naught star plus beta 1 plus beta 2 delta 1 times x1. So this will be our beta 1 star plus beta 3 plus beta 2 delta 3 times x3 plus epsilon plus u. So this will be our beta 3 star, and this will be our new error, our error term. What do we call it? Our eta. Okay. So any questions there? We've just derived the beta naught, the beta 1, and the beta 3 from basically how our estimates will differ from the true estimates. Any questions there? Okay. So I got a private question. When we group them, we take the coefficients with the same number. Yeah, so if you think about it, all of the coefficients on x1 are going to form this beta star. All the coefficients on beta 3 are going to form this beta 3 star. That's why we're grouping them. So basically that's, yeah, maybe that seems weird. Let me try to think of another way of explaining it. So when we group them, we take the coefficient with the same number. Yep. You're just grouping them in terms of what is on the same x, or they're all error terms, or they're all constants. If that makes any sense. Does that help a little bit? The idea, I think, is this is actually what the estimate is doing, is that there's going to be these influences expressing the coefficient on x1. Okay, awesome. So let me clean up a little bit. Feel free to take a screenshot. It will also be online in the YouTube video, but I've got to clear a little space, so feel free to take a screenshot if you want. 1, 2, 3, 4, 5. Okay, so that was letter A. Check. Letter B is, suppose that x2 has a positive effect on y. So that's to say, so for B we have beta 2 is positive. It has a positive effect on y. If delta 1 is greater than 0, delta 3 is less than 0, then will the coefficients on beta 1 and beta 3 be upward or downward biased? Okay. So remember that beta 1 star, the estimate that we're getting, is the true beta 1 plus beta 2 times delta 1. So is the beta 1 biased upward or downward? We're going to have a beta 2 that's positive and a delta 1 that's also positive. So what does that mean? It means the beta 1 star will be greater than the true beta. which implies that the bias will be upward. Okay, the bias is up. It's pushing. We're going to get an estimate that's too big. Okay, now let's do the same thing for beta 3 star. It's equal to beta 3 plus beta 2 times delta 3. And here we have beta 2 is positive again, but delta 3 is negative. So what does that mean? It means that our beta 3 star, so this whole term will be negative, okay, is going to be less than the true beta 3. So the bias will be downward. The bias is going to push the estimate down. Support your answer with the expressions you derived in part A. So that's basically what we're doing here, is that a positive times a positive is a positive. So we know that this chunk right here is some positive number. We know because beta 2 times delta 3 is a negative, this is going to be some negative number. So it's going to chip down beta 3. Okay. Any questions there? Okay. So beta 2, I'm sorry, B is also answered. Feel free to take a screenshot, but I'll also put this up on YouTube. Awesome. It really does help when you guys say, oh yeah, it makes sense, or not quite clear. That is really helpful just to know what the temperature is. Okay. Okay, so let's look at C. Suppose Y is income, X is years of education, X2 is work ethic, and X3 is parent income. Argue that the estimates of beta 3 and beta 1 are upward biased, downward biased, or unchanged to the omission of X2. Support your answer with both logic and the expression you derived in part A. So remember that, let's do beta 1 first. Beta 1 star is equal to true beta 1 plus beta 2 delta 1. So beta 2 is the effect of work ethic on income. Do we think that work ethic has a positive or a negative effect on income? You can message me privately if you're nervous about doing it in front of other people. Yep, I would think work ethic is going to have a positive effect on your income. Okay, delta 1 is the relationship between years, between your income and years of education. Do we think that years of education income have a positive or a negative relationship? Positive, thanks. So do we think that beta 1 will be upward bias, downward bias, or unchanged? Here we've got the beta 1 star will be beta 1 plus some positive number times another positive number. Okay, so that means that this chunk is going to be positive, and that means that beta 1 star is greater than beta 1. So it means upward biased. Okay, and that's actually what we're often worried about in estimates of education on income, is we're worried that the omitted variables are going to upward bias the effect of education. Yep, perfect. Thank you, Manuel. Thank you, Yesenia. Thank you, Devin. I really appreciate your participation. Okay, so let's do beta 3. Beta 3 star is equal to true beta 3 plus beta 2 times delta 3. We've already discussed the effect of work ethic on income. We think it's positive. What do we think delta 3 looks like? Do we think that parent income and let me think here. Okay, do we think that work ethic has a positive or negative relationship with parent income? That's a toughie. So I could see a case for positive. Yeah, I guess that's probably the typical one. A great counterexample is that for immigrants, for the children of immigrants, or children who arrived while they were immigrants who came to the States as kids, they're low income and very, very strong work ethic. I think in general, it's true that high income parent their kids are harder working, but there are groups for whom that's not true. So I could imagine either um, either sign. Yeah, so that's a good example too. So I also just think it's important to be able to make both cases. I could also imagine delta 3 equals 0. I could imagine anything basically on parent income and work ethic. So if it's 0, like let's just so that we don't do two of the same thing again, let's just imagine that work ethic isn't really related to your parents' income. Then what we'll find is that beta 3 star is equal to beta 3 plus beta 2 times delta 3, where this is positive and delta 3 is 0. So what that means is that beta 3 star will be equal to beta 3. And that means that our beta 3 is unchanged due to the emission of x2. Support your answer with both logic and the expressions you derive. So I might say, I think both cases true beta. So yeah, you're going to get the true beta 3, but not the true beta 1 if parent income and work ethic are unrelated. So you just have to say, I think that people with higher income parents tend to be harder workers. I think that people with, so I like, this is how I would think of it. Almost is like, yeah, I am actually like kind of now I'm very curious what hardworkingness looks like. Okay, so anything, yeah, whatever you say there is fine. But I would probably say, yeah, I mean, I know a lot of people with like very highly paid parents and they're super hardworking. And I know immigrants with very little money whose children are also very hardworking. So it's kind of a toss-up. So that's question C. You could write all three cases. Yeah, just explain, oh, like if this were true, then that. If this were true, then that. If that were true, then that. Yeah, you have three cases. Delta 3 equals 0, equals a positive number, equals a negative number. What are two reasons that work ethic might be omitted from the equation? So this is a really good question. So why is work ethic probably omitted from the equation? I think the fundamental, yep. The fundamental issue is that because it's hard to measure. How do I measure your work ethic? I'd have to like even if I gave you a little quiz that said like, okay, there's a couple things you could do. You could do a little quiz where you say, do you feel like you're a very hardworking person, a not very hardworking person, or a very lazy person? Well, those results are sometimes reliable, but many times not. Like Some lazy people think of themselves as hardworking. You'll find this is true in life. Many hardworking people feel that they're lazy, and that's part of why they are hardworking, is that they're trying not to be lazy. You could give people a little test that basically measures how hard they work in an hour. But how hard someone works in an hour might not be how hard they work day to day on important tasks. So it's very hard to measure someone's work ethic. Yeah. So I would say it's hard to measure, and you can give some examples about why it'd be hard to measure. It's hard to measure in a survey because people might not compare themselves to other people very easily. So like this is an example of where surveys are hard. Is there's this famous research about a thing called grit. And grit is kind of perseverance, like whether you're willing to stick it out even when it's hard. And so when we survey people and we measure how gritty are you, you say, oh, I never give up, I never surrender, or I give up easily. That actually tends to be very, very predictive of how well people do in their life. But what they find is that it's a little bit hard because some people that are actually quite gritty, they wish they were grittier. And so they say, I'm not that gritty. Or some people that are kind of easy to give up, they're not tryhards. They think of themselves as more tryhard than their friends or their family. So they score themselves very high. So that's one, yeah, surveys are very hard for that reason, because it's not clear who they're comparing themselves to in their mind. So that's the whole homework. So why don't you have a quiz tomorrow? I don't want to give you two things in one day. Why don't we have this due from next Monday? Due Monday. You're already done. So if you've kind of kept up on this homework, then you could just submit it right now. And if not, you have a few more days. You have the rest of today, tomorrow, Saturday, Sunday, and the rest of Monday, I guess, to turn it in. And then and it's easy points. It's great practice. I really want you to kind of go through the steps of these and make sure that this is clear. It's a really, 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 really important feature of the class, is understanding omitted variables bias. So that is all I've got. So I'll see you guys tomorrow morning at 9 a.m. And bring your questions. I will not have anything prepared. The only thing that I will be able to do tomorrow is to answer questions. So come with some questions, run into a brick wall this afternoon, looking at the notes, looking at your notes, looking at the slides, find stuff you don't understand and figure out what you don't get about it. And we will be able to iron that out together tomorrow. The reason that you have to come with a question is that it's very hard to hear an answer before you've asked a question. It is very hard to hear the answer before the question is in your body. So it's just a really, 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 really helpful thing to have the question, and then we can work from there. So there could be response bias. It's a little bit different than response bias. Response bias is whether or not someone is responding to the question, whether they're even picking up the survey to answer it. This would be something like, self-description bias. People don't describe themselves correctly. Will the session be recorded? I don't know. You'll have to roll the dice and find out. Levi back. I don't think I'm going to record it. This is just for kids that are studying early, preparing questions. And making it work. It's an incentive to study today. So, okay, well, class is dismissed. You're welcome to go and enjoy and pursue the rest of your day. And I will hang back and answer questions. Thanks all. Thanks, you guys. I really enjoy this class.